Alright, well, hello everyone and welcome to the MESA Robotics program. In this video today we're going to be talking about the major components of our robot, what they are electronically, and how we control them to make one whole functioning robot. So to begin, we have our standard DC brushless motors, and we use a pair of these to power our robot. And so the motors here, they are equipped with a plastic gearbox. You'll see this huge yellow piece right here, and then the actual electronic part is this little silver thing. So this is our brushed DC motor we use to actually drive the robot. Up front, we have the big yellow gearbox, which contains our reduction gear set, and then in the back, we have the actual DC motor part of it. And the gearbox itself contains a set of reduction gears, and what that does is it reduces the speed of our output shaft, and it also increases the torque at the output shaft. And the reason this is helpful is it allows these relatively small DC motors to power our relatively heavy bots, which are around 1 pound each. And so also when I mention the term brushed, you'll typically hear that when referring to different types of DC motors. And what happens is when you apply current to an electromagnet, it will attract permanent magnets, but then as soon as that attraction reaches the pole, it will stop. But for us, we need to cause continuous rotational motion. So we have, as you can see in this GIF here, 3 separate electromagnets arranged around the shaft here, and then we have 2 permanent magnets here. And so we apply current to all 3 of the electromagnets so that they rotate towards the desired pole. And then once they rotate to that desired pole, these brushes here contact the commutator, and then they switch the polarity on some of these electromagnets. And then that causes the ones that we're attracting to then repel, and it continues the cycle of attraction and repulsion to keep the rotational motion going. So to change the speed of our DC motors, though, what we need to do is apply different amounts of voltage. So with a digital system, which is the one we use to control this robot, they are either on or off. So in other words, there's no variable throttle, which is what we want. So instead what we use is an approximation known as pulse width modulation, or PWM. So essentially we have a voltage source that has a fixed amount at the beginning, but what we do is we open and close the circuit very fast. And so what this does is, if you look at the voltage over a period of time, the voltage will appear as if it's a fraction of the source. So even though we're opening and closing the circuit and effectively stopping the flow of electricity, the motor can't sense that because it occurs so quickly, so it just continues operating as if it were at a percentage of its full throttle. So also another important topic, if you continue in combat robotics, you may encounter another type of motor known as a brushless motor. And so to just go over this simply and briefly, you can think of them kind of as electrical engines. And so what happens is you have way more electromagnets and permanent magnets inside, and instead of being activated by physical brushes, what happens is you use an electronic speed controller, and that fires the electromagnets in a very specific and precise order. And so to increase the speed of a brushless motor, you don't actually increase the voltage, you just increase how fast the speed controller is firing each electromagnet. So to move on to our next component, or set of components, we have our remote controlled setup. So we have here our remote controlled transmitter. And this is a standard setup, 2.4 gigahertz from a RC car, basically. The pistol grip controls the throttle channel, and the steering channel is controlled by this little knob here. So once our transmitter encodes all the channel signals digitally, what happens is it takes all of the PWM signals and summarizes them into a single new signal known as pulse position modulation, which you can see up at the top here. And so PPM is, again, another type of digital signal, but in this case we're transmitting it over the airwaves since we don't have a physical connection between our robot and the transmitter. So it's essentially a series of square pulses with the total number of pulses up here corresponding to how many channels you have. And then the length between each of the pulses here corresponds to the PWM value for that channel. So to move on to our next component, we have the RC receiver here, this little one. And what it does is it takes the PPM signal from the airwaves and deconstructs it back into the PWM data for each of the individual channels. And so looking at the receiver, we have a set of 12 pins total arranged in 3 columns, and 4 rows. The columns from left to right are signal, 5-volt power, and then ground. So the signal is the set of pins that actually sends out the PWM pulse, which will control our devices. The 5 volts, you can use it to either power a circuit from the receiver or to power the receiver itself. And then ground obviously closes the circuit, and that's very important in our case because even though the PWM pins here are the ones that actually produce the signal, it won't go anywhere unless we have this ground pin connected, so that's very important to make sure you get. And then the next portion is we only use 2 of the signal pins on this receiver, the channel 1 signal and channel 2 signal, because those are the corresponding signal pins for throttle and steering. So next up is probably the most important component for our robot. We have the Arduino Nano here, which essentially acts as the brains. So what it does is it reads the data from our RC receiver, uses a bit of algebra to convert the PWM signals, and then outputs them in a different kind of PWM to our motor driver, which I'll discuss in a bit. So normally the type of RC transmitter setup that we have here is designed for an RC car, and that employs 1 motor for steering and 1 motor to provide power to the wheels. But our robot is unique because it uses 2 separate drive motors to actually go. And this type of configuration is known as tank steering, and you can see this is an RC car over here. It has 1 motor that controls the steering rack, and that's its drive motor there, but we have 2 of the same type of motors we use to power our robot. So to go forwards, we need both of our motors to spin at the same rate, and to turn, we need them to spin at different speeds and potentially different directions depending on how tight of a turn we want. So to do this in our code, we use a set of algebra equations to convert the throttle and steering inputs from our RC controller into the motor speeds for tank steering. But to actually get the throttle and steering signals from the RC receiver, we have to plug into the signal pins on channels 1 and 2 on the RC receiver. And to clarify, those are going to be these 2 pins in the corner here. So, but to begin that process, normally PWM is just a signal that you emit from a source and you use it to provide variable power to control something. But what we need to do is actually decode it and figure out what its value is between 0 and 255. So to simplify this decoding process, the Arduino looks at a very finite window of time, which allows it to discern the individual pulses of PWM. And so then what the Arduino does is it measures the time between the voltage going from low to high, and the length of this time corresponds to the PWM value, with a shorter period of time indicating it's staying at a higher voltage for longer, and thus it's closer to 255. So now that the throttle and steering PWM values are available and the algebra calculations are complete, we send them out to the motor driver in tank steering PWM through 2 specialized pins on the Arduino Nano. And speaking of which, our motor driver is the next component we'll be going over, which is this big one here. So this essentially acts as a translator between the Arduino Nano and the motors. It takes the desired speed that we want and applies it to a greater voltage while also handling more amps. So to clarify why that's important, sometimes you can simply hook up a motor to a PWM signal and it will run. But in this case, the motors that we are using, they would draw too many amps for our Arduino Nano to control directly. So to perform this special function, what the motor driver does is it behaves similar to what is known as an electrical relay. So this device is basically an electrical switch that's controlled by a lower voltage in this path here, but that lower voltage operates a coil here that allows a higher current circuit to flow. And that higher current circuit allows us to drive the motors without overheating the Arduino Nano. And so the PWM pins from the Arduino are the ones that control this function. And the pins from the Nano will connect to these end pins on the motor driver here. These very end ones. So to continue controlling the motors, we have to go over another concept, which is the motor driver's ability to act as an H-bridge, which is another type of electrical device, except this one can change the polarity of a circuit, or in other words, which direction the electricity flows. So this is useful for our robot because we may need to in case we need to turn or go in reverse, we have to, of course, reverse the direction the motors spin. So to represent this schematically, you can think of it as a circuit with 4 switches in each of the corners that create 2 parallel tracks, and you can see one highlighted here in red. And closing 2 of the switches on opposite corners, what that does is it causes the current to flow through the motor in one direction, but if you open these 2 switches and close those two, the current will flow in this direction, and since current determines the direction of the motor spin, that allows us to effectively reverse our motors. So these switches are a bit more of a complex deal, and they're controlled by 4 separate digital pins on the Arduino Nano that connect to 4 pins here, these center 4 on the motor driver. Alright, so we have our final component here, which is our power distribution board. We use this mainly because it provides an easy on and off switch for all of our electronics, but it also provides a specific amount of power that I'll go over here in detail. So the 12-volt battery pack that we use to power our motors is sufficient for the motors, but this voltage is actually too large for the Arduino Nano to handle itself, and the same is true for the RC receiver and the motor driver to an extent. Now, the motor driver does accept the 12 volts for the motors, but to control all of those special functions I was talking about, like the relay and the H-bridge, it needs a 5-volt logical circuit, which is something separate. So what the power distribution board does is it has a 5-volt regulator here, which is actually this component here. And what that does is it steps down a much higher voltage to a more reasonable 5 volts. And this is what allows us to power our smaller electronics. And also, the power that we give to this comes from a separate 9-volt battery as opposed to the 12-volt pack, because we wanted to avoid making too many connections with our main battery pack, just to simplify things. And so this is just kind of a summary slide to explain the signal flow that we're using for the robot. So again, we have our RC controller here that has throttle and steering in a physical motion, and then that's encoded digitally in PWM, and then the RC chip inside the transmitter turns that into pulse position modulation, and then that goes to the RC receiver where it splits it back into these 2 signals, and that goes into the Arduino Nano where we feed it into our algebra equations, and it goes into our different PWM for tank steering that finally goes to our motor driver. And so with that said, that's all of our explanations for our major components, and I hope you learned something today and help improve your robot building capabilities.